I'm very happy to introduce Evgeny Gorski, and especially happy that his subject is going to be the one he's going to talk about, because this seems to be like a very exciting area that has seen open question arising all over the place. And I know for a fact that Eugene understands many of these things much better than maybe I do in some instances. So I'm happy to listen to him. And I've heard him give great talk, so I'm sure that he's going to do well. Eugene is at UC Davis. They have an exciting group over there. So I'm looking forward when travel will resume so that we can actually exchange more than we do with the Zoom meeting. But in the meantime, we'll do with this one. So without further introduction, I will let Eugene tell us about this. Eugene has told me that if you have a short question you want to ask, you're welcome to open your mic and ask the question. If you want to put them in the chat, I'll look at it, and I may do so, open my mic and ask them for a question. But anyway, we'll have time afterwards for any other question. So Eugene, go ahead.
Right. Thank you so much for this introduction. So I'm honored and humbled. So I just want to say that I really love Montreal. I think it's a really beautiful city, and I like the city. I like all people there, all mathematicians there. So it's really a pity that I couldn't come and give this talk in person, but I really wish that in the near future I would be able to do so. So I'll talk about algebra, geometry, and combinatorics of some flavor of link homology. And so specifically, I will be talking about Khovanov-Rozansky homology, which is a pretty complicated theory. It was defined by Khovanov and Rozansky in 2005, more than 15 years ago. So they defined a triply great link homology, which I will briefly outline, but won't really define because it's very technical. And it generalizes so-called HOMFLY or HOMFLY-PT polynomial, which is much easier to define. And so I will not talk about the definitions, but I'd rather focus on general properties and some examples and some open questions which are related to this homology, and like what we understand, what we want to understand, what is the progress in understanding this homology, and maybe specifically types of questions that I'll try to overview are computations of Khovanov-Rozansky homology. So there is this complicated invariant. Can we actually compute it for some classes of nodes or links? What are the answers? Are there any interesting patterns in the answers? Are these answers related to some other parts of mathematics? Specifically, I'll talk about connections to t-Catalan combinatorics, which is a very rich subject in algebraic combinatorics. And Francois is one of the leaders of this study of t-Catalan combinatorics. Then I'll talk about some general structures in Khovanov-Rozansky homology. And what can you say and what the general structures tell us about combinatorics, maybe a little bit. And then for kind of the second half of the talk, I'll talk about some geometric models. And it turns out that for some classes of links, not for all links, but for some classes, you can give very concise geometric model. Basically, for example, you can find a space associated to a node whose homology is this Khovanov-Rozansky homology. And then you can study this space by methods of classical algebraic geometry or classical algebraic topology. And there is a lot of recent activity in this direction, which I'll try to overview as well. So just maybe we don't know how to compute the homology explicitly, but we can relate it to homology of some other space, which is kind of more tractable by more classical methods. So that is roughly the plan. And so I'd like to start with the HOMFLY-PT invariant, which kind of underlies all what I'm going to say. So this is invariant of links. It's to any link, it associates a rational function. It was defined in the late 80s by a group of 6 and 2 more people. Well, I guess I won't be able to list them all. But they're like the first letters of the last names are in this acronym. So this is so for every link you have a rational function in two variables a and q, and the rules to compute these rational functions are listed here. So whenever you see a crossing, so all the links are oriented, and whenever you see a piece in the link diagram which looks like this, you can replace it by this piece and by this piece, and whatever invariant you get for a link with this piece minus the invariant that you get for a link with this piece is equal to q minus q inverse times the invariance for this resolved piece with no crossing. And so this allows you to trade kind of positive crossings for negative crossings, and this is called the skein relation. And then there are two more normalization relations that if you see this kind of curl, this accounts to some power of a, negative a inverse, and you can undo the curl. And if you see a circle which is not linked and doesn't cross anything else, this is just additional factor of a minus a inverse over q minus q inverse. And so the basic theorem in the subject is that if you start from a link, using these rules, you can compute invariant of any link by simplifying this and kind of recursively simplifying the link until it gets trivial. And second theorem is that it's really a link invariant, so it actually doesn't matter how you draw the link and how you apply this recursion in which order, the result will always be the same. So it's really a link invariant. And so for any link, there is a kind of intrinsic way to do this. And then this is invariant is related to lots of other subjects. It's related to John's polynomial if you specialize A to be the square of Q. It's related to some other interesting polynomials in the representation theory, but we won't really need it. So this is kind of the underlying invariant of all this. Okay. And so what Khovanov and Rozansky really did, they wanted to so-called categorify this or generalize it to some link homology. So what is the basic structure of link homology? So to any link, now they say we don't associate the rational function in A and Q. Instead, we associate the vector space, which is called HOMFLY homology of the link. It is a triply graded vector space. So there are three different gradings, I, j, and k on this space. And it breaks as a direct sum of these components of degree I in the first grading, j in the second grading, and k in the third grading. And if you have a knot, this space is finite dimensional. If you have a link with several components, it might be infinite dimensional, and you have to be, it's finite dimensional in every grading, but it's kind of totally could be infinite dimensional, and we might talk about this. But the most important property why it's called HOMFLY homology is that if you take the Euler characteristic with respect to the third grading, with respect to the k grading, and take the generating function with respect to the other two gradings, so you have the sum of q to the I, a to the j, and minus 1 to the k, and then you put the dimension here. So this minus 1 to the k times the dimension is really kind of the Euler characteristic in this k direction. And then you recover some, in principle, series or polynomial in A and Q, and this polynomial agrees with the HOMFLY polynomial that we discussed on the previous slide. And so in this sense, you say that the coefficients of the HOMFLY polynomial are either dimensions of some spaces, or more precisely, alternating sums of dimensions of some spaces which come from this theory. And so the main problem with this theory is that it's very complicated. And so they defined it in 2005. It was a really long time until people computed interesting non-trivial examples. And I won't say much about the definition, except that it's quite involved. It uses the theory of Zorgel bimodules, which is very interesting subject in commutative algebra and representation theory. And then for every link, you associate a complex of Zorgel bimodules, which I'm not defining, and then you apply Hochschild homology to that. So it's very, very involved definition. But it turns out we won't need it at all for the talk. So I just black box the definition and say there is some theory, and I just want to study the properties of this theory, what we actually know and what we actually want to know about this. Okay, so that will be kind of my approach in this talk, that we won't really go deep into definitions, but we want to overview. And so one basic question is, okay, so there is this big complicated theory, what can we actually compute? And so here's one example, and this example was instructive for me for last 10 years. So I've been thinking about it and different properties of this picture, definitely for like last 10 years. So on the left, you see the 3-4 torus knot. So this is a knot, which is drawn here. And you can think of it as drawn on the surface of the torus, where you go in one direction 3 times and in the other direction 4 times. So this is kind of the straight line on the torus wrapped around. And that's how it looks like. So that's very concrete knot. And so you take this knot, you put it into this machine of Khovanov-Rozansky homology, and the output is this picture on the right. So the picture on the right is actually taken from the paper of Gukov, Dunfield, and Rasmussen from also around 2005. And when they wrote this paper, it wasn't even known that Khovanov-Rozansky homology can be defined. So they conjectured the existence of this HOMFLY homology. And then soon after, Khovanov and Rozansky defined this. So, but so Gukov is a physicist and Dunfield and Rasmussen are 2 great mathematicians. So they conjectured that if HOMFLY homology exists, it satisfies some structural properties, and the structural properties allowed them to reconstruct this picture on the right, which I will explain. Soon after, Khovanov and Rozansky defined this homology, and actually while after, people confirmed that this prediction is correct, and the homology indeed looks like this. And so what is represented on this picture? So the homology is a triply graded vector space. So in this case, the space is 11-dimensional, and every dot on this picture represents one basis vector in this vector space. So every dot is a generator in Khovanov-Rozansky homology. Now, how to read this picture? So you have the horizontal direction, that is Q grading. So one of the gradings which we had before. You have the vertical direction, that's another grading. So they determine the 2 gradings. The position of the dot determines 2 of the gradings. Then these numbers represent the 3rd grading of this corresponding generator. So for example, this guy live in Q degree 0, A degree, I guess, 8. So the bottom line has A grading 6, and they go up by 2. And then the 3rd grading would be 5, because the number 5 is here. So there is some way to read all this grading from the picture. There are all these arrows, which I'm not going to explain at all, but they are important, and they were important for Gukov, Dunfield, and Rasmussen here. And so that's it. And so if you don't know anything about Khovanov-Rozansky homology, if you don't know the definition, but you see this answer, you can say, well, so did we see this answer before? Can we identify like what do these numbers mean? And can we identify like all the combinatorial information encoded in this picture here? And so one basic observation is that if you look at the rows of this picture, we see the 5 dots on the bottom row, we see the 5 dots on the next row, and we see the 1 dot on the top row. And so they arranged like 5, 5, and 1. So again, the total dimension is 5 plus 5 plus 1, which is 11. And so I think for me, the first thing when I saw this picture was that we actually saw 5, 5, and 1 in different combinatorial contexts. Namely, you look at the pentagon, and you look at all possible ways to draw non-crossing diagonals in the pentagon. So there are 5 ways on the bottom row to draw 2 non-intersecting diagonals in the pentagon. So they allowed to be intersecting at the corner, at the vertex, but not in the middle. And so in the bottom row, we just have triangulations of the pentagon. There are 5 of them. And in general, the number of triangulations is called the Catalan number. And on the next row, you see the ways to draw 1 diagonal in the pentagon. And again, there are 5 of them in this case. And then on the top row, there is 1 way to draw no diagonals in the pentagon. So this is just 1. And so in some sense, this picture matches the previous picture, at least like on some very naive level, that you see 5 things here and 5 things here and 1 thing here. And so one would imagine that this basis in homology represented by this picture, so you can find a bijection between these dots and the triangulations and partial triangulations of the pentagon. And so this was a conjecture. And so I conjectured something along these lines in 2010, and it was proven by Matt Hogenkamp and Anton Mellet only quite recently, not so recently now, in 2017. And the result is the following. So first of all, the total dimension of this Khovanov-Rozansky or HOMFLY homology for a special class of nodes. So you have n plus 1 torus node. So again, you draw on the torus, you go n times in one direction and n plus 1 times in the other direction. And the total dimension is equal to the number of ways to draw non-intersecting diagonals in this n plus 2 gon. So if I had 3, 4, then we had diagonals in the pentagon, as we should. And so in particular, if we arrange them by number of diagonals, this matches how we arrange the HOMFLY homology by this grading and by these rules in some sense. And we have much more information because so on the bottom row, for example, we had the Catalan number of things, the triangulations, and there is a well-defined thing called t-Catalan number, which depends on two different parameters q and t, which was defined by Garcia and Heyman. And the theorem says that the bigraded dimension of the bottom row of HOMFLY homology for the n plus 1 torus node is equal to this t-Catalan number. So if you go back here and you look at the bottom row, you can actually read all these gradings and all these dimensions from the t-Catalan number. And more generally, if you have more general torus node, the situation is slightly more complicated, but there is a notion of rational t-Catalan number depending on two numbers m and n, and the bigraded dimension of this bottom row is given by the corresponding rational t-Catalan number q and t. Let me say a couple of words about these t-Catalan numbers and what they do. t-Catalan numbers and their rational analogs were introduced and studied by many people. So Francois is one of the leading experts in this area of combinatorics, and also they were studied by Adriano Garcia, Mark Heyman, Jim Haglund, and many other people. And so one definition of these t-Catalan numbers is the following. So you take a rectangle m by n, and then you draw the diagonal in the rectangle. And let's assume that m and n are co-prime so that the diagonal doesn't go through integer points. And then you look at all possible lattice paths which go below the diagonal, which never cross the diagonal. And they go from this vertex to this vertex. Then to such lattice paths, one can associate two statistics called area and dinf, which I'm not going to define. But then you sum over lattice path, and then you say that you have q to the power area, and sorry, that should be t to the power dinf. And this is a function of two variables q and t, which is this t-Catalan number. And so then the previous theorem, you can say that, well, so first of all, this lattice path, if you have n by n plus 1 rectangle, they're in bijection with these triangulations, and that's a very classical fact in combinatorics. In general, we just have the basis of this bottom row given by lattice paths, and if you want to read the grading of every given lattice path, you look at the area and dim statistics. So that is the content of that previous theorem. So this is very explicit. You can program it on a computer, you can compute it. So in this sense, this theorem on the previous slide gives you complete answer what happens in the bottom row. And there are also answers for the other rows, which are slightly more involved, but not that much involved really. And so t-Catalan numbers are related to wealth of different areas in mathematics. They're related to combinatorics of Macdonald polynomials and shuffle conjecture in algebraic combinatorics by the work of Heyman and other people. They're related to the geometry of Hubert scheme of points on the plane, and I'll mention a little bit of that in the end of the talk. They're related to representation theory of double affine Hecke algebras and Cherednik algebras and elliptic hole algebras. And so they keep appearing in different areas of not only combinatorics, but also algebraic geometry and representation theory and even mathematical physics. So they're related to lots of things. And all these things actually give you different ways to compute rational Catalan numbers. So again, I'm not giving any formulas, but I'm saying that, for example, the first way, relation to this Macdonald polynomials and shuffle conjecture, you can express it in terms of either the sum over the lattice paths with some statistics, or in terms of some operators on symmetric functions. But the geometry of the Hubert scheme would give you a completely different formula where you have a giant sum of rational functions, for example, in Q and T, and that adds up to a polynomial. And representation theory of elliptical algebra says they need to take matrix element of some operator in Chernykh algebra in some representation, and I'm not going to say anything about that. So overall, I just want to say that there are lots of ways to compute it. And so we know HOMFLY homology of the torus nodes up to now, and you can use it as a kind of testing ground for all possible questions about link homology, because that's a rich and interesting family. And I just want to mention some recent work of Nakagane and Sana. So they programmed Khovanov-Rozansky homology using some, there were some programs, but they weren't that good. And in basically last year, Nakagane and Sana wrote a different program with some computational tricks, which computed HOMFLY homology for all nodes up to 10 crossings and most of 11 crossing nodes, except for like very few where it's really taking a long time to compute. And so this is a wealth of data, and they definitely include all torus nodes in this family, but you can go ahead and look for combinatorial structures there and various other structures for this homology. So in this sense, now I think computationally and combinatorially, we have a lot of data to look at and lots of data to analyze. Okay, so that was about combinatorics, and we'll come back to this in a little bit. Next, I want to talk about the general structures in link homology. And one structure which is kind of evident if you look at this picture is the symmetry of this picture. So this diagram is clearly symmetric with respect to the vertical axis. And that is not a coincidence. So the symmetry was observed in all this data that people studied. And it was definitely conjectured by Gukov, Dunfield, and Rasmussen back in 2005. But it took very, very long time to prove. And we proved this last year with Matt Hogan, Campanat, and Millet, that indeed HOMFLY homology is symmetric around the vertical axis. So you have the symmetry which flips the picture like this. And moreover, there is an action of the Lie algebra SL2 in HOMFLY homology. And so the generators of SL2, they would go horizontally. They would kind of jump from here to here, then from here to here, then from here to here, and backwards. Then another sub-representation will go from here to here and to here. So they jump kind of 2 steps horizontally. And for any node, you can define an action of the Lie algebra SL2. And then it's well known that finite dimensional representation of SL2 are symmetric. And so this symmetry is the symmetry that we're looking at. So not only we have the symmetry, we have a bit more. We have this SL2 action. And in particular, this means that the dimensions kind of tend to grow to the middle to this vertical line in the middle. Okay. And so this symmetry became the proof used a lot of machinery. But one immediate consequence is that for torus nodes, this implies that these t-Catalan numbers are symmetric in Q and T. And that is not obvious at all. So there are combinatorial proofs of this fact, which essentially use shuffle conjecture, some relations to shuffle conjecture. But it's a very, very hard fact. And if you look at the definition of this t-Catalan number with lattice pass and area and dinf, it's not obvious at all that the result is symmetric in Q and T, and somehow it's a very hard combinatorial problem to see this directly. But this not theoretic approach, in some sense, it gives you, combined with this computation of link homology via Catalan numbers, it gives you yet another proof of the symmetry. So that is interesting, but maybe. Yeah, so symmetry is very interesting. Right, so I want to say a couple of words about links. So we won't need it that much, but if you have a link with several components, HOMFLY polynomial is really not a polynomial, it's a rational function with some denominator. You can expand it in a power series in Q, but then this power series will be infinite. And so as a consequence, HOMFLY homology is infinite dimensional, but it has a lot of structure. So in some sense, it has more structure than you would have for nodes. And so one reason why it has a structure, so more or less by definition, it's a module over the polynomial ring in R variables. when you have one variable per each component of the link. And that just follows from construction, which I'm not explaining. And so you can ask, well, is this symmetric in any way? So is the symmetry extending to links? And directly, it couldn't be, because it's infinite dimensional, and somehow it's hard to flip infinite dimensional representations. But also, you have these x variables, and the symmetry doesn't take x variables to x variables. So if you have a module over some polynomial ring, and then it couldn't be a module over some other polynomial ring with some different gradings somehow. So that was a major problem. And so with Matt Hogenkamp, we defined a slightly different version of link homology for links with many components called yification of HOMFLY homology. And for that yification, we have additional variables y1 through yr. So for each component, now we have two variables, x1 and y1, and then x2 and y2, and so on. And another thing which we proved in the same paper as Matt and Anton is that so the original HOMFLY homology is not symmetric for links, but if you yify, if you kind of add these extra deformation parameters, then the yified homology of any link is indeed symmetric, and the symmetry exchanges x's with y's. So there is a rich commutative algebra, which I guess I'll show in the next slide. And somehow, I mean, one reason why links have more structure than nodes, because you can study the module structure over these polynomial variables in x's and in y's. And it's great that everything is symmetric and you can really swap x's with y's. And that was kind of one of the main motivation for us to define this yified homology. And here's one example. So this is again an example, but I couldn't explain this before because it's really complicated infinite dimensional space. And so to explain the answer, we need all the structure. And so we consider an n-torus link. So what is an n-torus link? We have n unknotted components. So all these components are just trivial circles, and every pair of circles is linked once. So for example, if n is equal to 2, it's just this Hopf link. If n is equal to 3, I have 3 circles, and they're pairwise linked once. But the circles are kind of normal round circles, not knotted, not anything. And so in this case, we have a link with n components. We expect that the homology is again a module over n x variables and n y variables, and we want to identify this module. And the answer is pretty complicated. And so what we proved in 2017 is that if you do this yified homology of this n-torus link, the answer is the following. So you take polynomial ring in two n variables, x1 through xn and y1 through yn, and you look at the intersection of ideals generated by xi minus xj and yi minus yj. So for each pair I and j, which are distinct. So intersection of ideals is again an ideal. And so this is something complicated ideal inside the polynomial ring, which is definitely a module over x's and y's. And so that is the answer. So that is the yified homology of this link with many components. If you want to, you can try to write graded dimensions of different pieces of this ideal, or write some combinatorial formulas, but it won't be as easy as before because, again, the ideal is definitely infinite dimension. And one way to see this ideal and to understand it is to say that we have n, so you have C2, this is complex two-dimensional plane. You have n points on C2, so with coordinates x1, y1, x2, y2, x3, y3, and so on, up to xn, yn. And then each of these ideals says that xi is equal to xj and y is equal to yj. And so this is really an ideal saying that 2 points labeled by I and j collide. And intersection of ideals, as we learn in basic algebraic geometry, corresponds to the union of the corresponding varieties. And so this is really the ideal for the union of all possible diagonals in C2 to the n where pairs of points collide. And so this is very natural object from the viewpoint of commutative algebra and algebraic geometry. And this ideal was studied by different people. We point out that there is this kind of interesting relation between commutative algebra and homology of this link. But again, it's less combinatorial, but more on kind of commutative algebra side of things. But after all, like if you know this answer, we can go back and compute the character and dimension of this homology. And if you want, so this was all about this Wi-Fi homology. So on the previous slide, I said that it's symmetric and the symmetry exchanges x's and y's. Of course, this is symmetric and the definition is symmetric in x's and y's. So that was a very nice example showing the symmetry. And if you want the original HOMFLY homology of the n-torus link without the y's, you just cancel them. So you quotient by the ideal generated by all the y's. And then another theorem that it indeed works, this ideal is actually free over these y variables and you just quotient by them and you don't lose any information. Okay, and so just I wanted to show this example to illustrate that for links with many components, the answer on the one hand more complicated, but on the other hand, sometimes you can use some commutative algebra tricks and compute them like this. Okay, and I think that's all what I want to say about the examples and structures. So maybe I'll pause for a second and ask if there are any questions.
Is there any reason why this works only for n-torus links, not the general links in S3?
I mean, something works. So you would definitely get a module over these x's and y's. You just don't know which module. And like identifying this module is a hard problem. If you have another n kn torus link, there is a similar answer. If you have a torus link with several components, so like mn, but m and then a not coprime, there are lots of results in this direction. I think it's not complete. So like we know the dimensions, for example, of all the components, but we don't know the module structure as far as I know. So
how about links that are not torus links?
Yeah, so some things like, I mean, for some small examples, it's known, but again, I mean, the major obstacle is that you have infinite dimensional vector space. So even like coding this is a computational problem because you need to like count dimensions of infinitely many things. And you need to kind of either work with modules over large polynomial rings. And there are some programs which do this, but this is very, very slow. Or like the main advantage of this program that I mentioned for nodes is that you know a priori that the answer is finite dimensional. And so you don't need to deal with these commutative algebra issues. And if you have a link, then again, in principle, there are some programs and you get some answer, but they're very limited as far as I know, and it's hard to compute. But the general theory tells you that just you have a module over x's and y's, and there is a symmetry which exchanges x's and y's, but it's not enough to determine the module, but sometimes you have some other methods to say something, but I think there are lots of open questions here. Just like I give you random link, I don't know, but like you give you any link with two components, I get an interesting module over two x's and two y's. What is the module structure? There are lots of open questions there. There are some expectations when the answer is known. There are lots of expectations when the answer is not known. So I think there is a lot to be explored here, especially for links. Yes.
I see. Thank you.
You can there are lots of famous like Borromean rings, which are where you have three circles. All of them are unknotted and pairwise unlinked, but the whole thing as the three circles is linked together. Like from the general theory, you know that you have a module over polynomials in like 3x's and 3y's. Which kind of module? I don't know, and I think nobody knows the answer. So that is kind of like just basic question, compute more examples and see how this works. So that is a big open challenge for links.
I see, thanks.
Okay. All right, so let's keep going. So next I want to overview some geometric models for link homology. And for some of you, it might be more interesting or less interesting, I don't know. So the first geometric model is given by so-called Braid varieties, which were studied by many groups of people and very actively in the recent couple of years. So start from the Braid group on n strands. So recall that the Braid group is defined by n generators, which we call sigma 1 through sigma n minus 1, with relations given here. So sigma I, sigma I plus 1, sigma I, sigma I plus 1, sigma I, sigma I plus 1, sigma I, sigma j, sigma j, sigma I. And so if I have for every sigma I associate a matrix, which is drawn here. So I have ones on diagonal, except for a 2 by 2 block, 0, 1, 1, z, which depends on a variable z. And this block is at i's and I plus first position. So one can just check that the following identity of matrices holds. So if I take bi of z1, bi plus 1 of z2, bi of z3, it's the same as bi plus 1 of z3, bi of z2 minus z1, z3. There is some interesting change of variables here, times bi plus 1 of z1. And so in this sense, this corresponds to a Braid relation, except that we need to do some change of variables between z's on the left and z's on the right, change the order, kind of add this term, but there is a bijection between the variables on the left and variables on the right. This is just easy linear algebra computation. So given a positive Braid, so it's important that the Braid is positive, and you can write it as a product of generators, sigma I1 up to sigma k. We can define the Braid variety. So what is the Braid variety? We take, for each crossing, you put this matrix at the corresponding position, depending on, so each crossing has its own variable, z1 up to zk, if I have k crossings. And I put this extra variable with ones on kind of anti-diagonal by some technical reason. And then I want this product to be upper triangular. So this is a very elementary definition, which you can teach to undergrads. So again, this is like if you multiply all these matrices, I have k different variables z1 through zk. So I have a giant matrix and all the entries are some complicated polynomials in the z's. And I require that this is upper triangular, meaning that just I require that all these polynomials below the diagonal vanish. So this is some very explicit algebraic variety in k-dimensional space with coordinates z1 through zk. And you can study this variety. And so one basic thing which we proved last year in a couple of joint papers with Roger Casals, who's also in Davis, myself, my brother, Michael Gorski, and Jose Cimental, is that this variety is either empty, that could happen for some small beta, or it is a smooth manifold of expected dimension. And what is the expected dimension? We have k variables here, and we have n choose 2 equations. So the expected dimension is k minus n choose 2, and it is a smooth manifold of this dimension. So everything is good. Then it depends if beta closes to a node or not, and there are some subtleties. If it's closest to a link with many components, as similar to the subtleties we had before. But if it's a node, we can actually factor out some torus and get some y of beta, whatever. Maybe that doesn't matter that much. And so the main theorem here is that actually this is a model for linear homology. So this goes back to the work of Webster and Williamson, and then revisited recently and rephrased in these terms by Anton Mellet and Mintam Trin, that if beta closes to a node, then you can actually compute HOMFLY homology or Khovanov-Rozansky homology by taking the homology of this variety or of this variety. So just quotienting by this torus. And there are a few things here. So first of all, it's important that you have a node. So beta closes to a node. If it doesn't, then you need to take equivariant homology with respect to some torus. But that's also not too bad. And more importantly, so this is about the bottom row of HOMFLY homology. It has 2 gradings. And the gradings here are the homological grading and so-called weight filtration defined by Deligne. So this is a smooth, non-compact algebraic variety by the work of Deligne. There is so-called weight filtration in cohomology, and then you need to take it, and that would give you the second grading. And I'm not going to explain how this works, but maybe just a comment. So somehow, if you use this variety, it has a smooth compactification, and you can compute the homology using that smooth compactification. And then this main substance of this theorem is that actually agrees with the definition of Homfly homology, which I didn't give you through Zorgel bimodules. So somehow you can really see Zorgel bimodules here if you know well the geometry of Lag varieties and Bot-Samuelson varieties and things like this. But maybe I won't comment more on this. I just want to show a couple of examples to show how explicit it is. So again, like this is very, very explicit thing. This is like the best you could hope for in some sense, because just multiply matrices and say that the product is upper triangular. And so one example, which I personally like, is that if you have two strands and the braid is just the cube of the generator, so sigma 1 cube. So this corresponds to the 2-3 torus knot. And so here's the answer. So you have Z1, Z2, Z3, and then 3 variables, and then one equation, which is Z1 plus Z3 plus Z1, Z2, Z3 is equal to 1. And so that is some very, very explicit equation, and you can study this variety, compute homology, and then it turns out that this homology is related to Homfly homology. And so in this sense, if I, so I didn't define what is Homfly homology, but if I just tell you this, you can take it as a definition for positive braids. You can say, well, take a positive braid, compute this variety, compute its homology. That is the Homfly homology. You still need to prove that it's not invariant, but that's maybe a separate story. So this is something like very, very explicit. Another example, which is, I think, really beautiful, was found by Galashin and Lam also last year. So if you look at the torus knot example, which we'll all like a lot, and which I explained before, then this variety up to some torus is isomorphic to so-called open positroid variety. So this is an open subset in the Grassmannian defined by non-vanishing of cyclically consecutive minors. So every point in the Grassmannian you can represent by m by n plus m matrix, and you look at all consecutive m by m minors, and they all are non-zero. So this is a variety which was studied by many people in cluster algebras, in geometric representation theory, and combinatorics. And so this is just a very explicit open subset of the Grassmannian. And so what they say that you take this thing, and then you compute the homology of the space, and this is the homology of the torus knot. And so again, if you want to have all the gradings, you need to put the weight filtration, which is a bit subtle, and then the homology of the space is given by Q t-Catalan number, which we discussed before. So that is their main theorem. And what's interesting is that it's not known how to prove this theorem geometrically. So I think that's another challenge for the subjects right now, that somehow the way they prove it, they have reduced the problem to compute a knot homology. So they again compare the space to this Braid variety, they compare the space to the Zorgel bimodules and definition of Homfly homology, and then they actually use the fact that knot homology is computed by Q t-Catalan numbers. So it's not that, like in this case, geometry tells you the answer for knot homology. It's like knot homology tells you the answer for a geometric problem. And I think this was really kind of surprising for me. And I still would love to know like how to see all the beautiful Q t-Catalan combinatorics in this particular example. And it's like very, very explicit variety, like how to compute its homology. That's all. Like why the size of homologies given by Catalan numbers, why all homology is supporting even homological degrees, for example. That's another interesting feature here, which is not obvious. And so I think there are lots of open questions here, and this is just one class of knots. But I think these varieties have great potential in understanding. And we had a couple of papers about them and studying relations to other interesting varieties, to positroid varieties, to Richardson varieties, to brick manifolds of Loris-Kabar, to other spaces and some properties. But I think like in terms of homology, there is a lot to be done here. So we know some basic geometric properties like smoothness or other things, but like there is a lot to be done here. Okay. So that is the model of braid varieties, and this is defined for all positive braids. Another geometric model, which is a bit more technical, but historically it was much earlier than this one, and it was like well developed before this. So this is related to so-called affine springy fibers. So affine springy fibers are important in geometric representation theory and in number theory. They're related to orbital integrals for various groups. And the definition is roughly speaking the following. So you pick a matrix, n by n matrix. It depends on one parameter t. And then you look at all possible subspaces in n-dimensional space over Laurent polynomial, Laurent series in T. And you require that the subspace is invariant under multiplication by T, or V is so-called the lattice in this space. And then in addition, you require that it's invariant under multiplication by our matrix, gamma of T, which we regard as operator on this n-dimensional space over Laurent series. And again, people starting from Kazhdan and Lustig and many other people, and Go and Yun and lots of other people studied these spaces. And it was observed, and I'll say it in the next slide, that these spaces are actually related to knot invariants. And so how they're related to knots, first of all. So if you have such a matrix gamma, what can you do? You can, first of all, write the characteristic polynomial for this matrix. That would depend on two variables. So if every entry of the matrix depends on T, and Y is kind of lambda, the parameter for characteristic polynomials, the equation would depend on two variables. So for example, if I start from this matrix, 0, T cubed, 1, and 0, I write characteristic polynomial, this will be Y squared minus T cubed. And so Y squared minus T cubed on the plane Y and T defines the cuspidal curve like this. And then the classical construction says that you take this cuspidal curve, it lives on C2, so this is a 4-dimensional real space, and then you take a small sphere, which is 3-dimensional, and intersect it with the curve. So as a result, in the intersection here and here, you would see a knot. So this is called an algebraic knot corresponding to this algebraic curve. And so if you start from any matrix, gamma of T, you can definitely write this algebraic curve. And if under some assumptions on gamma, you can assume that you have like only singularity at 0, and then this is determined by this knot. And then you can start to ask, well, how this gamma, like what kind of algebraic information about gamma is related to topological invariance of the knot. And so here are some examples. So one concrete example is generalization on of the previous page. So you take the matrix where you have zeros on the main diagonal, ones right below the diagonal, and then T to the M here in the corner. You can compute the characteristic polynomial and just Y to the N minus T to the M. And the corresponding knot is the again Mn torus knot. And so in this case, the homology of the affine Springer fiber was well studied by many, many people. And one thing which we observed with Misha Mazin is that in this case, the homology of affine Springer fiber with additional grading agrees with t-Catalan number. And actually, in this case, the proof was very explicit, because in this case, the space admits the cell decompositions. The cells are labeled by the lattice path that I mentioned before, and the dimension of the cell is somehow seen by the statistics of the infant area. So in this case, we see the homology pretty easily, precisely because the space is this. And again, like a posteriori, the homology is related to link homology because both are related to t-Catalan number. And of course, our work was motivated by earlier work of Oblomkov, Rasmussen, and Schende, who conjectured that for all gamma of T satisfying some really mild assumptions that all eigenvalues of gamma are distinct and some other things, you take this affine Springer fiber and you take its homology, and it's isomorphic to the HOMFLY homology of the link of the curve. So again, you start from gamma, you build a curve, from the curve you build a link, from the link you build the HOMFLY homology by some mysterious procedure, and the result is the same. And so in particular, the homology of this variety is expected to be the same as the homology of the Braid variety, which we saw before. And that is not obvious at all, and this is wide open conjecture, except basically for this torus knot case where we compute everything and it matches. as some people might know, if the link has several components, then this means that the curve has several irreducible components. So if the characteristic polynomial of gamma has several irreducible components, a fine springy fiber is much more complicated, and it has infinite, like it has much more complicated structure. You have lots of irreducible components, and this kind of shows up in the fact that HOMFLY homology is infinite dimensional. So, in kind of naive level, this matches, and you can make it a bit more precise for links as well. And maybe another remark, which I want to say here, is that also you can look at this curve and study some. So you can phrase this affine springy fiber just in algebra geometric terms as the moduli space of some torsion-free sheaves on this curve, but maybe that's not so important. Okay, great. And so this is another model. Again, I have another space whose homology is expected to be link homology. It's pretty limited because not every knot can be obtained this way. There are not so many knots which you can draw this way. There is a called algebraic knots, which you can get from algebraic curves, but still it's an interesting class, and we expect this homology to have somehow better properties than generically chosen knot or link. Okay. And so the last thing which I want to mention really briefly is the third geometric model, which is given by the Hubert scheme of points on the plane. So I will not define the Hubert scheme of points on the plane, but I just want to say that we have C2 to the n. So these are n tuples of points on C2. You take the quotient by the permutation group by the action of Sn. This is very singular. And you take resolution of singularities. This is called the Hubert scheme of n points on C2. It's a very important variety. It shows up in mathematical physics as the moduli space of instantons. It shows up in geometric representation theory as quiver variety of Nakajima, and it shows up in many other contexts. And so, roughly speaking, what we expect is that for every braid beta, you expect a vector bundle, or maybe a sheaf or complex of sheaves, and one needs to be very careful here, on this space. So the space is fixed. The space does not depend on the braid now. The space is just the Hubert scheme of points. But what changes is the vector bundle on the space. And for this different vector bundle, depending on the braid or on the link, you compute the space of sections, or more precisely, sheaf cohomology. And that is supposed to be related to HOMFLY homology. So this is kind of less direct than the two previous models, but computation, it's actually very good because algebraic geometry gives you a lot of tools to compute this space of sections. And the two gradings in this case, there is no kind of homological grading, or there is, but it's kind of plays a different role. But the gradients correspond to scaling. So we have a two-dimensional plane. We have a scaling action of C star square, which scales coordinates. It acts on C2, it acts on C2 to the n, it acts on this quotient by Sn, and it leads to the action on the Hubert scheme. And so these two gradings give you an action on the space of sections, and that's what we want to understand. And so the constructions of this F beta are very different and very involved, and I'm not going to go into that. But there was one construction which was given in my work with Andrei Negut and Jake Rasmussen. There was a related construction in my work with Hogenkamp. And there was a very different construction which was proposed by Blomkov and Rozansky in a series of papers, which constructed F beta by some matrix factorizations. But again, it's all pretty involved. So there is a construction. Again, the question is how computable it is, and like, can we compute some examples and see what's going on? And so that's what I'm going to say. So two examples which are kind of easy to explain, or at least to state, is the n plus 1 torus knot, which I started from. So the corresponding sheaf is the following. So you take the punctual Hubert scheme, where all the points collide into one, and then again you look at the resolution of singularities there. On this space, you have a natural line bundle, which is called O of 1, and you compute the space of sections of this O of 1 on this space. And that space actually was studied by Mark Heyman, and he observed that t-Catalan number, which is supposed to match the homology, agrees with the space of sections of this line bundle on this space. And so in this sense, this like what happened on the previous slide is a deep generalization of Heymann's result. He's saying, well, t-Catalan number you can realize as the space of sections. And we know that homology can be realized as a space of sections. So that works for this class of torus knots. Maybe this works for any knot as well. And so that is what happened on the previous slide. And another example, which is harder to say, but also very important, is that if you have a torus link, the vector bundle has rank n factorial now. And this is related to so-called Precesi bundle and the gain of 1. And by another work of Heymann, the space of sections you can compute, and this is the intersection of ideals xi minus xj, y minus yj, which we saw before as the homology of this NN torus link as a module over x's and y's. And so again, the answers match. And so in this case, we can just guess the answer by utilizing this high non-trivial results of Heymann. But in general, there is some machine and some procedure defining the sheaves in vector bundles, at least abstractly. And I think that's almost all. I'm almost out of time, and that's almost all what I want to say. So I want to say two things. So there was this paper of Nakagami and Sano that I mentioned, and I think it's very nice. So it's called Computations of HOMFLY homology. They have a kind of user-friendly introduction of how to actually compute HOMFLY homology by definition without much machinery. And they, like, if you go to their paper, they have a link to the folder with all the data for all the nodes up to 10 crossings. So if you're interested in the data and like just going through it and trying to spot some patterns and trying to check some things that I said today for some small nodes, that's a place to go. And I think it's very nice, very concise paper for this. And then if you want to know more details, and more references for these geometric models, for the structures, for the relation to t-Catalan numbers. So we wrote a survey paper with Oscar Khovanov and Jose Cimental. It's called Algebra and Geometry of Link Homology. It's an archive, and we have tons of references and tons of kind of specific examples there, which kind of surveys what is known and what is not known about this link homology. And I think I will stop here. Thank you so much.
Yeah. So thank you very much, Eugene, for a wonderful picture of amazing direction that can be explored here. Are there any questions by people in the room? So I'm looking. Please, if you have a question, raise your hand so that you come up at the top so that I can see you. Oh, I have one question here, Franco.
Hi, Eugene. Thank you very much. It was a very nice talk.
Thank you.
So at the beginning, towards the beginning of your talk, you defined the homology, and you said, let's use this as a black box for now. So I guess my question is, what more information would you get if you actually knew more of the details or the structure of this homology? Like in terms of, like, I guess we started off with these polynomials, right?
Yeah, so you have examples where you have, for example, the same polynomial, but different homology. So actually this paper of Nakagami and Sano, they have like some very specific examples. So here's a knot. We know that like the HOMFLY polynomials are the same, but homologies are different. So if you're just interested in, for example, distinguishing knots, then that's as good as it is. You can ask like what extra information it is for like from topological point of view. And it hasn't been like that much explored for HOMFLY homology. It has been explored a lot for other flavors of not homology like Khovanov homology. But you can ask again, what is, for example, the spread of this homology? Like what's the maximal degree where it is non-zero in this direction or in this direction? And there are some results about this. And there are some bounds, but again, in general, it could tell you something interesting about the link. You can ask, for example, does it tell you anything about like the minimal genus of surface bound in the link in 3D or in 4D? And there are some results about this, mostly in Khovanov homology, but in this as well. So yeah, so besides this, there are applications of this to topology which are also very important. And maybe I want to mention, so for people who have seen Khovanov homology, so this is different. So this homology is different, but there is a spectral sequence relating this homology and Khovanov homology. So in principle, you can recover Khovanov homology from this one. And so all the beautiful applications of Khovanov homology, they're somehow packaged in this one, although it's hard to get them directly, I guess.
Thanks.
So are there any other questions from the room? Gabe Frieden, you can unmute yourself. Yeah.
Oh, sorry. Hi. Thanks for the very nice talk, Eugene. I was wondering. So I really like this this idea of the braid variety, and then this very nice example with the torus knots being the braid variety is the open pository variety. Are there other examples of knots that give you sort of very nice varieties like that are known?
Yes. Yeah, the answer is yes. So you can get, so this is the open positoroid variety. There are lots of other positoroid varieties in the Grassmannian. And you can get all of them from knots. Like if you give me a positoroid variety, there is a way to write knots, a knot which corresponds to that. For any Richardson, open Richardson variety, you can do that as well. So
in type A or in any?
In type A, all this in type A. Yes, all this what I'm saying is in type A. So in principle, you can define like knot homology in other types, I guess.
I see. So this is like sort of a type A. Well,
yeah, this is like a type A construction. Again, like you can ask which of these things generalize to other types, but this is not completely done for sure. Ask like if you replace the braid group, but braid group of other type.
Right.
Like that's I guess what you're asking about. There are some results in this direction, but it's just much more complicated.
Yeah.
And like none of this combinatorics is available, none of this. But you can do something. But yeah, but like if you want to stay in type A, that for example, one thing which we proved in that paper with Casals, my brother and Simmental, is that any positoroid variety, you can draw 4 different braids and all of them give the same positoroid variety. So if you have positoroid on like M, Kn, in this Grassmannian Mn plus n, then you have some braids on M strands, you have some braids on N strands. They look differently, but you can write them like in very clear combinatorial way. And all of them, the corresponding variety is the positoroid variety. So that's pretty explicit. And again, like you can ask, I think like one question which is very interesting, like very actively studied, is that if you have in the opposite direction, if you have a braid, like do you have nice properties? Like do you have a cluster variety, for example? Like all these things are known as to be cluster varieties. Like do you have a cluster variety from any braid or from some class of braids? And there was a lot of progress. So there was a work of Gauss and Wang in this direction, and there was lots of other conjectures as well. But yeah. And then you can ask, what is the cluster structure? What does it have to do with this link homology? And that, I guess, nobody knows. But that's a very good question. But yeah, if you're looking for examples, like, yeah, so in the second paper, we have lots of examples and lots of pictures of knots and positoroids. And if you're interested in this, yeah, that's the place to look.
Okay.
So there is a question in the chat by Igor Shelukin. Could you please say a bit more about the sheaf over the Hubert scheme coming from a braid? You mentioned that there are different construction. What is the simplest one?
I don't know what's the simplest one. I'll tell you my favorite one. So you can think like the Hubert scheme, you can think of as a blow up of this. So in some precise sense, you can take the singular space of C2 to the n mod Sn, and you blow up kind of all singularities at the same time. And so because it is a blow up, you can write the homogeneous coordinate ring of functions on the space. And so this will be big graded algebra. And so the construction says that for any braid, you construct a graded module over this graded algebra. And then this gives you a sheaf on proj of this graded algebra by algebraic geometry. And I think, I mean, I can explain better, but it's not written here, so I couldn't write on the screen. Yeah, but like, I mean, basically, again, the idea is that to any projective or quasi-projective, in this case, variety, you can associate a big graded algebra, and proj of this graded algebra is the Hubert scheme. And so basically, we construct explicitly, like in what our approach with Nikud and Rasmussen, and especially in the paper with Hogenkamp, we explain how we start from a braid and get a module over this graded algebra, and therefore get the sheaf. And so one property which is easy to explain is that if you have a braid and you add a full twist to the braid, what happens to the sheaf? So like in the previous models, actually, it's a very hard question. What happens to the braid variety if you add a full twist or something? But in this model, if you add a full twist, your sheaf is just multiplied by O of 1. So you can think of this example, for example, as you take n, 1 torus knot, which is unknot and which is easy to compute, and then you add a full twist, and then you add an extra O of 1. Here again, you n torus link, you can start with the trivial braid, add a full twist, and get, so for trivial braid, you get purchasive. For trivial braid times O of 1, you get purchasive. For trivial braid with a full twist, which is n torus braid, you get this purchasive times O of 1. And so, and then you can keep adding this full twist and you get lots of different braids, and somehow that is a way to study like how this braid changes if you add, how the shift changes if you add off once, and then this proj construction somehow matches everything together. That's kind of the flavor of what's going on. So it's very indirect. It's not like you just tell you that there is a sheaf, but yeah. So that is roughly speaking what we do. And then what Oblomkov and Rozansky, they do very different things. So they say that there is some very complicated bigger space which kind of is hanging over the Hubert scheme. And then they construct the sheaf there by some kind of working with matrix factorizations and convolutions and things like this. And then basically once they do it for a big braid, they just push it down to the Hubert scheme and get the sheaf. But yeah, I mean, but their construction is very, very technical. So, but it's kind of more direct in this sense. And conjecturally, we get the same result. So I don't know if I answered the question, but it's hard to do without writing.
The answer is I see. Thank you.
Okay.
Are there any questions from the room in general? Maybe I have one that, in a sense, you alluded to just a minute ago when you said that you had a full twist. So there are operations on knots that give you new knots from before. So it's interesting to translate this into construction in any of the approaches that you describe. I understand from the point of view of elliptical algebra, but there's other. So in the Hubert scheme, what you answered was
you just multiply by O of 1, yes.
Yeah.
In the Hubert scheme, you multiply by O of 1, sorry.
Yeah.
Right, and then for braid varieties, I don't know. I think it's a very good question. What happens for braid varieties? For this thing, you just take gamma and multiply by t.
Mm-hmm.
So if you have the matrix like this, you just multiply every entry by t, you get a new matrix, and you can check that that corresponds to it in a full twist to the braid.
And then you probably you can extend many other operators, say in the elliptical algebra in these contexts.
Yes, I mean, you can hope to extend, but like, I mean, in many cases, you can draw them like on not series side, but like in this model, like, I don't know how to do. I mean, the full twist is now being understood, but yeah. But then you can ask like all sorts of questions. So for example, like, I mean, from what I just said before, so if you start from gamma and just multiply it by t, that's kind of one full twist, and multiply it by t again, that's another full twist, and so on. So you have a giant, I mean, you have an infinite collection of these affine Springer fibers for gamma, t square gamma, and so on. And you can study this whole collection of spaces and their homology, and what acts there, what are interesting operators, and We have upcoming paper with Khovanov and Oblomkov about this. Let me just advertise that. But it's complicated. So, and then in this language, so it's easy to write the matrix for the full twist, but it's not clear what it does to the space somehow. And I'd love to know what happens. But for people who know cluster algebras, this is like going from a n, for example, cluster variety to n plus 2 cluster variety. How do you do this geometrically? I don't know.
So are there any other questions? If not, thank you again, Eugene, for a wonderful picture of all these great questions. Thank you.
Yeah. All right. Thank you.
Okay.
Bye.
Goodbye, everyone.